Hi, this is Connor for Avid Visions, and today I'm talking about this photo fact of the week, which is about Moire aliasing and what the difference is between the D800 and the D800E, which is one of Nikon's new full-frame cameras. So first I will be talking about Moire. Now, this is a term that's used to describe error in the reproduction of an image or the image that your camera captures. So moire is when you're taking a picture of something that has a really high frequency or spatial frequency. So that means there are a lot of lines that are really close to one another and are very small in the picture. So this will crop up a lot of the time in like really fine fabrics with a lot of lines. Moire is actually a term that originates from the fabric and textile industry. Or say if you're taking pictures of a glass building with a lot of windows, it's far off in the background of a landscape picture. You'll notice, especially if you're just looking at the picture on a small LCD screen on the back of your camera, that there'll be some weird patterns that kind of pop up in the building's windows, and it doesn't look like quite the right lines all the time. This also happens a lot in bug's eyes if you're a macro photographer. So that's what moire is, and it is all a product of this next term, aliasing. Aliasing has to do with how your camera reads input signals. So I'm going to try and explain that over here using these two graphs. Okay, so say we have this input signal right here. So we see that this x-axis represents the distance on your sensor, right? So the 0 on this x-axis corresponds to the 0, like the first row of pixels over here on this box that I'm using as a sensor, and the 6th row of pixels would be right here, right? So let's just divide up this sensor really quickly. For 0th row, 1st row, 2nd row, 3, 4, 5, and 6, right? So let's label it 0, 1, 2, 3, 4, 5, and 6. So in real life, we have light is an analog signal, right? So we're going to say, oh, in this area we have a really bright light, so maybe we have like a light bulb right here. And then it drops down to whatever's over here. There's no light. This is just light, so this is also really intense. This is more an illustrative purpose. It's just, think about the further away you get from the 0, the brighter the light. That's how I'm illustrating this here. So, if we say that this light pattern is the same in the vertical direction of the sensor, say this is the same in all parts of the picture, you'd end up with a pattern kind of like this on the sensor, right? We have really bright areas here, a really dark area here, because we don't have any light at the first row of pixels. It's going to be bright here, and bright here, and again, dark in the middle, right? So we see that this input light pattern that we made corresponds to this image over here. Now let's look at this second input pattern, right? So again, we have the same kind of sensor layout. We have the 6-pixel sensor I've drawn over here. We'll divvy it up again. 0th row, 1st row, 2nd row, 3rd row, 4th row, 5th and 6th rows. So again, 0, 1, 2, 3, 4, 5, and 6. Okay, so we can clearly see that this signal is much different than the previous signal, right? This one has a much higher frequency. It oscillates up and down a lot more quickly than this one does. But because our camera is only actually reading the input signal at each specific pixel, right? Each finite little point. It's not reading all of the in-betweens. It samples right here, it samples right here, it samples right here, here, and here at each pixel, right? We realize that we actually are going to end up with, well, I'll draw it out. So, at pixel 0, we have a high light intensity, so this is going to be bright. At pixel 1, right here, this is supposed to be a 0, so we have a 0 at pixel 1. At pixel 2, we're really far away from the x-axis again, so we're calling high intensity, right? That's a bright light. And pardon me, I shouldn't have drawn these graphs to go negative. It's not actually a light intensity, it's an amplitude of the electromagnetic waves. So that is my problem. But anyway, now we're going to look pixel 3, we have another 0 value, so draw that in. 5 is also 0 value, and then we see that 4 and 6 are actually high. So now we can zoom out a little bit, and we're noticing that these two completely different input signals give us the exact same picture. And this is what aliasing is. When you have two signals that have different frequencies, and one pixel is kind of exceeding it's called the Nyquist rate, but a rate for safe sampling, you can get the same picture. If we had a more finer level of detail, like more pixels in here, right? Like say we had twice as many pixels, so we had like something there, something there, something there, something there, there, and there. We'd have a dramatically different picture, right? And if we did the same thing on this image, you see that these two pictures that we come out over here on the sensor with would be entirely different. It's only because of aliasing that these look the same. So aliasing is when you don't sample at a high enough sampling rate, or like you don't have enough pixels to sample a pattern correctly, so you get something that doesn't actually look like the input pattern, but instead looks like something completely different. And if you want another way to think about this, something that you've definitely all seen in your life, think about when you're on a highway looking at a car's wheel, or if you're looking at a video of a car's wheel. Say we have a piece of tape on this wheel, right? And the wheel is spinning in this direction. I'm sorry, I realize this blue is probably very difficult to see. The wheel is spinning in this direction, right? So, if you have a video camera, video cameras say we're taking a picture once every 24 frames per second. I'm sorry, yeah, 24 frames per second. So, video camera, your video camera takes one picture, one frame of the video, every 1/24 seconds. So, say this wheel is spinning at just the right speed, so that after 1/24 of a second, our red dot, or our red piece of tape, has only rotated back around this far, right? So in the time in 1/24 of a second, the wheel has traveled only that much. Then, the next 1/24 of a second, it's only going to travel that much again. And so on our second frame, the tape ends up here, then here, then here, then here, then here, right? You see we're sampling, we're taking a picture, or sampling, just a bit too slow for the wheel's rate. So even though the wheel is actually spinning this way, the way we see the tape moving, it looks like the wheel is spinning the opposite way. That's another example of aliasing. It's where we are seeing an other frequency. Alias is some Latin root of other. So that's what aliasing is. And you might be wondering, okay, well, what does this have to do with the D800 and D800E? Well, that's where the low-pass filter comes into play in a camera. So a low-pass filter is a filter that only allows low-frequency objects to pass through it. So that's kind of like saying, we know that our camera can accurately sample this signal. We are defining this as a tolerable signal. If something is oscillating this quickly, where it goes from a maximum to nothing to a minimum in 2 pixels, we're saying that's as high of a frequency as we can go. So that's allowed. So this will say arbitrarily can go through the low pass filter, but this, because it's a higher frequency, doesn't get passed through the low pass filter, right? It only passes low frequencies. So, in most cameras, you have a setup like this, where you have this low pass filter will take care of horizontal frequencies. So, it smooths out the image so that the very high frequency noise doesn't get through. So, light will come through here, and it gets split up a little bit in the low passing. Then this is a wave plate and infrared filter. This just gets rid of light that you can't see. That's the infrared part. It gets rid of that. And it also, this wave plate shifts the wave so that when it hits the second low pass filter, instead of getting bounced right back into itself, it gets split this way. Right? You see that our last filter split it horizontally, this one splits it vertically, because this one is a vertical. And the low-pass filters are actually the exact same. The wave plate is responsible for shifting the light so that this one acts, the second one acts vertically and the first one acts horizontally. This one just changes the orientation. This is also called the hot plate, by the way. So that when the light strikes the sensor, it hits 4 pixels instead of just 1, right? Because we now have these 4 beams of light. And then those pixel values can be averaged to make the image. Now, this is a normal camera setup. But the D800E is a little bit different in that it gets rid of the wave plate, right? So there's no wave plate. That means, and the low-pass filter is also a little different. That means that, I'll move down here to illustrate it. We have our first little filter here, hot plate, the second part is the infrared part. I do have this red color actually, okay. Yeah, so infrared filter, second low pass filter, and then we're going to say the camera sensor is yellow just because. So this is the D800E over here. So light comes in through the first low pass filter, splits up again, right? Wave filter here doesn't do anything actually. That's part of the difference of the D800, D800E. When we get here, the light actually recombines into a single pixel. So we've basically gotten rid of the low-pass filters. And you might say, well, aren't we at risk for Moire now because of aliasing? And we are at risk of aliasing. But the thing is, the D800E has 36.6 megapixels. So we have such a fine granularity and a high sampling rate that it's very unlikely that you would find anything that isn't manufactured or man-made to have really close together lines that will ever cause an aliasing issue with this camera because the sensor is so sensitive. And the advantages of this is when we have this low-pass filter and when we have 4 beams of light hitting a sensor at once, we're averaging values and you lose sharpness. So in most cameras, when you don't have a ridiculous amount of megapixels, you can sacrifice the sharpness to make sure that you don't get all these like messed up patterns that aren't true to life. But on the D800E, which is designed for studio environments when you won't have these crazy moire patterns, you can get rid of the low-pass filters to have increased sharpness. And that's why the D800E is an option. So, I hope this video has been informative to you. Again, please comment with anything you'd like to see in future weeks, and thanks for watching. See ya.